This is CPE 133. This is experiment 8, and what we'll be doing in this experiment is designing a 4-bit up-down counter. The objectives of this experiment are to basically understand a finite state machine. So we will be designing a finite state machine in this experiment kind of at a medium level. A low level would be a gate level, which we don't do anymore. High level would be behavioral modeling, which we'll get to next. Additionally, in this experiment, we need to use a clock division module, which is important because there's a clock on our development board which is at 100 megahertz, which is pretty fast. But when we do stuff that we want to see, we have to divide that clock down considerably. So once again, we're designing a finite state machine based 4-bit up-down counter. We're going to use a button to select whether it counts up or down. This counter has two different types of outputs. One of them is decimal and the other one is Stone Age unary. And both of these outputs are Moore type outputs. Additionally, this is an experiment where we don't have to simulate it. We will verify it's working properly by just looking at it. So this model has 3 distinct boxes in it. There are 2 decoders. These are decoders, so they're combinatorial circuits, and then there's the state registers. So for this experiment, you will use a register template for the state registers. You don't need to design that, but you do need to design these 2 decoders right here. In this experiment, the outputs, as far as the output decoder goes, they're both Moore type outputs. You have both a decimal output and a Stone Age unary output. The decimal output is going to feed into this 7-segment display module, which is going to allow you to put it on the board. To see it on the board, it's going to automatically multiplex the displays. Second thing is, because we want to see this count, we need to slow down that clock divider, and a big description of that is on the next page here. And finally, we're just going to verify this is working by just looking at it. So there is a clock divider module out there, and essentially the problem is the system clock frequency, or we'll say the clock frequency on the board is 100 megahertz. Now what we want to do is slow that down to something around 2 hertz. Using the divider I call out in this experiment, you're not going to be able to get 2 hertz, essentially because it divides 100 megahertz by 2 to the n, where n is the integral value. But you can get it close to that. Close enough anyway. Anyway, the important thing is that it slows the clock down enough so you can see it count. So here's the input 100 megahertz frequency. Here's the divided frequency. What you do is this n value is a parameter. You override the parameter when you instantiate the clock divider. This clock divider also has this other input, which is the F clock only. Essentially, if I map that to a 1 when I instantiate it, it bypasses the clock division, which is very useful when you're using the simulator. If you're trying to use the simulator with a clock divider, it's really hard. You've got to wait forever to get a signal to change because the clock frequency is divided down. Okay, so if you put a 0 for that F clock only, it is going to be a normal clock divider. So this is going to be very useful in this experiment. So it's like with any experiment, you should design this on paper first. Keep in mind that you are pretty much responsible for designing the 2 decoders in the state machine, which is the next state decoder and the output decoder. 2 outputs are Moore type outputs. But make sure you don't design the register. It's just a register. Grab the register template. There are some other notes in the lab manual as well. Be sure to check those out. So you have some choices here. There's many ways to do this, and you have the option of instantiating the register. You need to do that, but you can also use these decoders as separate modules, or you can design them in line as always blocks on one level. So you're going to instantiate a register, but how you handle these decoders is up to you. You can make them separate modules and instantiate them if you want, or you can put those decoders all on one module. In this experiment, I don't see any great advantage to using one or the other.